So good afternoon, everyone. In an effort to stay on time, I'll do the little bit of housekeeping just a minute before the official start of the session. So welcome to this session, which is on water quality with a focus on nutrients. My name is Maria Strack, and I'm at University of Waterloo. As you probably know by now, we're going to have a pretty fast-paced session with a series of 10-minute talks, followed by a couple of two lightning talks at the end. And so I do want to remind everyone that there is a poster session tomorrow on Wednesday. So I encourage you to check out those posters tomorrow. For the presenters, do your best to stay to your 10 minutes. I will kind of come and make some noise at 10 minutes if you're still talking. If there's a little time at the end, we can take some questions, but I do encourage the audience to use the chat function at the bottom if you have questions for the presenters. And then that way, if we don't have any time for questions, presenters, please have a look and you could answer those questions directly in the chat. So it's my pleasure to introduce our first presenter, Meyer Shafi, who is presenting on phosphorus dynamics in urban sewer sheds. And I will turn it over to you.
Thank you, Maria. Can you hear me fine?
I can hear you well.
Yes, thank you. Hello, everyone. I'm so pleased to be here. I'm going to share my screen.
That looks good.
Yeah, perfect. Thank you. Thank you. So the session is about nutrients, and I'll be talking about phosphorus in urban landscapes, and the focus is on speciation, bioavailability, and export. Before I start, I'd like to acknowledge the contribution of my co-authors, funding agencies, and stakeholder partners involved in the project. Stormwater runoff is known as a main exporter of phosphorus, a nutrient that exists in different forms: particulate, dissolved, inorganic, organic, bioavailable, non-bioavailable. However, understanding about phosphorus cycling in urban landscape is quite limited, especially in the context of stormwater management design. Therefore, we conducted fieldwork, lab analyses, and modeling to provide insight into phosphorus composition and magnitudes in urban landscapes and highlight the management implications associated with that. There's a number of study sites in the project. There's one small sewer shed or urban catchment, as we call it, in Richmond Hill, Ontario, which is fully residential. There are two sewer sheds also in Ajax, Ontario, that are mixed. And there's commercial, institutional, residential, industrial, all within the same parcel of land. And the idea here is just to assess the impact of land use on phosphorus export and speciation. We also monitored the stormwater pond in Richmond Hill, where we took water and suspended sediments from the inlet and outlet. We also took sediment cores from bottom sediments of the pond, and the idea is to analyze phosphorus cycling as water moves through the system and as sediment ages. There's also a bioretention cell in Mississauga, Lake Wilcox in Richmond Hill, which has an urban drainage area. So I recommend that you take a look at other presentations in the conference by our colleagues in the project. In the lab, we measure a suite of phosphorus. Lab analyses, dissolve analyses give us total phosphorus, dissolved reactive phosphorus or DRP, and total dissolved phosphorus or TDP. Among them, DRP is the readily bioavailable form. Within the particulate phosphorus pool, we measure bioavailable fraction by sodium hydroxide extraction method. And within the same pool, we have a sequential extraction method called CDEX that gives us different pools of phosphorus within particulate form. And the idea is just to look at highly reactive pools within the particulate form in different places and see if we have more reactive or more less reactive or stable forms in the sediment. We had a lot of challenges in data collection in fieldwork, so there was a lot of gaps in our data time series. So we developed a multiple linear regression model to fill those gaps and also to forecast in future and hindcast in the past. So I'm not going to go into details of these models, but at the end of the day, this two-step MLR model gave us loadings of different species at the event scale. We use this model in the calibration and verification mode to make sure that model is transferable to other timeframes in the past, and we use that to make long-term predictions. There's also swim modeling coupled with phosphorus reactive transport modeling, which is ongoing. Sarah, one of our next presenters, is going to talk about the steps taken so far on that front. So when we looked at long-term predictions, when we compared these three sewer sheds, we noticed that Richmond Hill, which is a fully residential sewer shed, had the highest export, normalized export of total phosphorus, as you see on the top right panel. However, when it comes to DRP, the readily bioavailable form Ajax West, which is just the middle panel, had the highest export, and Ajax West is the sewer shed with the highest highest fraction of commercial landscapes and green spaces. So we see that land use has an influence on phosphorus export and speciation. Looking into particulate phosphorus pool, comparing these three sewer sheds, we see that Richmond Hill has the smallest amount of particulate phosphorus, but within that pool, we have the highest fraction of bioavailable phosphorus. So that means that residential development might have eutrophication potential because there's a lot of particulate phosphorus leaving the system. And if they're not captured by a P-retentive option like Stonewater Pond, they might be problematic down the road because there's a large fraction of bioavailable pool within them. Looking at the pond, our mass balance analysis showed high retention of phosphorus species. Around 70% of TP and DRP were retained, which is great. We also looked at the sediment and suspended sediment in the inlet outlet. And we noticed that as water flows through the system from inflow to the pond and to outflow, we have a smaller fraction of highly reactive phosphorus pools that are shown with black box in this figure. We also see that the calcium-bound phosphorus, the light green bars in this figure, increases down the core. So it's a stable pool, and it's great for retaining phosphorus in the system. So in a combination of these results show that this pond is actually performing well with respect to phosphorus retention. Just going quickly to the conclusions, we see that landscape actually has a major influence of phosphorus speciation. We notice differences in speciation and export among three catchments, and that's why we have to go with catchment-specific implementation of options to retain phosphorus. So we can't just use a particular stormwater management strategy for all catchments of different ages and different landscapes. We also see that ponds can be, and not always, consistent with the design goal. And the design goal is just to have high retention of phosphorus. And in there, we realized that chemical processes such as precipitation of calcium phosphate phases that resulted in high fraction of calcium-bound phosphorus is underappreciated. So design has to include that in it. The reason why we are able to draw these conclusions is because we have the ability to run CDICs. It's the state-of-the-art technique providing insight into phosphorus bioavailability and reactivity, and our work is a unique application in urban areas. So we propose that such a strategy is used in other sewer sheds to get a holistic view of phosphorus speciation in urban landscapes. Our reactive phosphorus modeling is ongoing, as I said before, and we will present that in upcoming venue. So that was a quick overview of some of the results so far, but I'd be happy to entertain any questions and follow up some conversations after the meeting.
Thanks very much. And we do have a minute or two. If anyone has a question, you could feel free to unmute yourself and ask, or you could add it to the chat. I don't see any coming, but I have a quick question about the age of that retention pond and whether you think the ability, like the strong performance, is related to the age of the pond at all.
Yes, so this pond was dredged in 2006. So whatever information we have is as of 2006, basically past 14 years. It's a retrofitted pond, so it's not a typical standard pond, contractor type pond. So it's expected to have high phosphorus retention. However, even 14 years of age and the level of retention that we see is quite good. So we would believe that these ponds, if they are not really old, like they're not close to being full, they can really retain phosphorus well, especially if chemical processes are enhanced in the system.
Yeah, good. That's great. Well, thanks very much. I think we'll move on
Thank
to the
you
next
for the
presenter.
opportunity.
Okay, so our next presenter is Sergey Bokniov, who's going to be presenting on a phosphorus net balance can in-lake processes explain reeutrophication in Lake Erie? And Sergey, we can't hear you yet. See your screen. We can't hear you, Sergey.
Okay, can you hear me?
Yes, we can hear you now. So yeah, I don't know if you had started, but you might want to go back to the start.
Okay, so can you see my screen?
Perfect, yes.
Excellent. So in my presentation, I would like to show how a long-term net mass budget for total phosphorus can be employed to better understand the major driving forces likely responsible for the observed eutrophication symptoms of Lake Erie. Lake Erie is a large, relatively shallow lake located on the border between Canada and United States, and is a very significant source of drinking water for more than 11 million people residing within its watershed boundaries. Lake Erie experienced very high pollution loads in 1960s to such an extent that in late 1960s, it was declared the dead lake. To deal with that, in 1972, the United States and Canada signed an agreement, the so-called the Great Lakes Water Quality Agreement, to control external phosphorus loads and reduce them to a level not exceeding 11,000 metric tons per year. This target load has been reached relatively quickly by early mid-1980s. And from the mid-1980s to about mid-1990s, you can see those like mid-1980s to mid-1990s, Lake Erie ecosystem recovered with noticeable improvements in water quality. However, since mid-late 1990s, there have been numerous observations of declining water quality conditions and reappearance of strengthening eutrophication symptoms. Amongst those observed eutrophication symptoms are the toxic cyanobacterial blooms in the western basin, nuisance green algae cladophora in the eastern basin, and hypolimnetic seasonal hypoxia in the central basin. It is generally accepted that lake eutrophication is largely driven by increasing excessive amounts of external loads of phosphorus. However, in case of Lake Erie, the external nutrient loads are declining and currently not exceeding 9,000 to 10,000 metric tons of phosphorus for most of the years. So the driving forces behind the reappearance of eutrophication symptoms are not clear. The net mass budgets of phosphorus can be extremely helpful to understand better the triggers of eutrophication. To understand such triggers, we constructed the mean 2003 to 2016 net mass budget for total phosphorus. Our hypothesis is that if the external loads are important, then over the long term, 14 years, they should be balanced by the losses. Alternatively, if that is not true and the losses exceed the external inputs, then the additional inputs, or so-called internally mobilized phosphorus loads, are needed to maintain the balance. The construction of a nutrient budget was achieved in 4 major steps. As the first step, we delineated the entire Lake Erie watershed into a number of the standard subbasins based on the subbasin levels, such as tertiary subwatersheds in Canada and 8-digit hydrological unit codes in the United States. Based on the watershed delineation work, we constructed the conceptual diagram of sub-watersheds within Lake Erie system boundaries shown on this slide. You can see those watersheds numbered with number 2. This is like Canadian watersheds, and numbered with number 1. This is United States portion of the watershed. As a next step, using the previous diagram of delineated sub-watershed, we constructed the mean water budget by estimating all water fluxes through the system from all those sub-watersheds. For example, here you can see the mean annual water fluxes expressed in cubic meters per second per year for all major processes affecting water budget, such as, for example, inflow from Lake Huron, watershed runoffs, number 2, water diversions, for example, water diversion, this is Welland Canal or some water intake from Lake Huron water. You can see also like precipitation and evaporation fluxes, and also consumptive use and groundwater recharge. For example, consumptive use and 5 and 6. Next, using our water budget, we constructed the mean total phosphorus budget for 2003 to 2016. This conceptual diagram summarizes all results and shows all fluxes expressed in metric tons per year for all major processes, such as, for example, Lake Huron outflow, tributary loads. For example, here we have tributary loads. We have atmospheric deposition, for example, number 3, sedimentation, outflow, and water diversions. Our budget indicates that system is not in balance with nutrient losses significantly exceeding the external loads. So additional loads are necessary to balance losses with the inputs. You can see those red arrows showing with the numbers. So these numbers expressed in metric tons per year. To meet the equilibrium conditions, such additional loads must account to 220 metric tons for Lake St. Clair and almost 3,300 of phosphorus for Lake Erie, all 3 basins of Lake Erie. It is not possible to construct a more detailed budget by splitting the entire Lake Erie budget into basin-specific budgets if interbasin water and nutrient exchanges are taken into account. The more detailed budgets revealed that none of the 3 basins were revealed that none of the 3 Lake Erie basins were in balance between the losses and the inputs. And you can see those like the large arrows on the bottom. So this is internal load, or so-called internally mobilized phosphorus amounts are needed to sustain balance between the losses and the inputs. Those red arrows indicates the effect of those internal loads on the downstream basins. So this amount, for example, for the West Basin amounts about 500 ton, and this stone would be finally transported to the Central Basin and further downstream. So such additional inputs or internal loads must account for 500 for the West Basin of Lake Erie, about 800 metric tons for the Central Basin, and almost 2,000 metric tons for the Eastern Basin. So what are the conclusions from our study? First, that in-lake phosphorus concentrations are not in balance with all losses and external inputs. Therefore, to sustain an equilibrium, there must be large additional fluxes of internally mobilized phosphorus. These fluxes represent a significant component of a nutrient budget and may be responsible for triggering and sustaining observed eutrophication symptoms. The additional load accounts for about 1/3 of all external inputs, which is well compared to the amount of externally supplied dissolved reactive phosphorus from the watershed and atmosphere. Such loads are of different magnitudes, so they are largest in the Eastern Basin, smaller in the Central and Western Basin, and the smallest in Lake St. Clair. And additional work is needed to understand the potential basin scale sources of this internally immobilized phosphorus. Okay, thank you. So this was my last slide.
Perfect. Thanks very much, Sergey. We don't have any time for questions, but like I had said earlier, feel free to use the chat and the presenters will be happy to have a discussion with you there for any questions that you have. So we'll move right along. Sergey, if you can stop sharing, we'll move right along to Lamissa Malik, who's going to continue discussion of phosphorus in the Lake Erie Basin.
Thank you, Maria. Starting to stop.
Yeah, just
no.
I can see only like new share, share, and how I can stop the.
I don't know if tech support can force that, or Lamissa, if you try, will it let you share or no?
Now I can do that. Wait.
Perfect. Yeah.
Can you see the presenter?
Yep, it looks perfect, and we can
Okay.
hear you well also.
Okay, thank you so much. I am Lamissa Malik. I'm a PhD candidate at University of Waterloo in Civil and Environmental Engineering. Today, I'm going to share my research titled as Legacy Phosphorus and Eutrophication in the Lake Erie Basin. So, okay, please. So Lake Erie is most pronounced among the Great Lakes due to its recurring algal bloom since 1960. And as Sergey mentioned, the algae grows when the lake is enriched with the nutrients. We term this as eutrophication. Nutrients are added to our landscape from agricultural activities, and nitrogen and phosphorus are the main nutrients responsible for algal bloom. And the phosphorus is the primary element for the algae growth. So the eutrophication has been linked to drinking water advisory, oxygen depleted condition, beach closure, death of fishes and pets, and its overall threat to the ecosystem. And several management strategies have been implemented on the Lake Erie watershed over the year to improve the water quality. And it started with Great Lake Water Quality Agreement in 1972. Detergent phosphorus was banned and wastewater treatment plants were upgraded. As a result, we saw a dramatic decline of total phosphorus input, and water quality had greatly improved. So no algal bloom was reported between those 1980 to 19 year. However, by 2000, the algal bloom had returned into Lake Erie. So to mitigate this recurring problem, Ohio Phosphorus Task Force recommended the 40% reduction goal by 2025. But after all these measures, the eutrophication is still persistent in lake, and you see those green bars, so higher the magnitude is a severe algal bloom condition. So these raises questions about our ability to set realistic water quality targets with conventional management plans that didn't account for phosphorus legacies. So another question comes, how do we estimate those legacies? To estimate the effect of legacy phosphorus that is accumulated in our land due to past human activity, we conducted a simple phosphorus mass balance. The primary phosphorus input are from agricultural runoff. This agricultural runoff is induced due to excessive use of fertilizer and unmanaged manure. Urban sources also contribute to phosphorus inputs. It includes household waste and laundry and dish detergent use. There are some minor contribution of atmospheric phosphorus deposition as well. Phosphorus from all these sources reach to our watersheds, and crop uptake is our only output source, as crop takes up phosphorus from the land, which helps to grow. So our phosphorus surplus is basically calculated by subtracting crop uptake from all the phosphorus inputs, and we use mostly census data for those collection of input data. So over application of this fertilizer and manure in agricultural soil have resulted a buildup of phosphorus surpluses over time. This building up of phosphorus in the landscape can be termed as legacy phosphorus. These legacy storage can slowly reach to the stream over the year and cause a delay in improvement of water quality. So let's look at some results. So we developed 86 years of mass balance studies for counties in the Lake Erie Basin from 1930 to 2016. The mass balance revealed that inputs to Lake Erie Basin has been increasing over the year. The warmer color here represents higher magnitude. Lake Erie Basin are dominated by fertilizer and manure in agricultural areas and in domestic wastes in urban region near Detroit and Cleveland. At present, inputs to Lake Erie Basin on western side is dominated by fertilizer, and eastern side in Canada is dominated by manure phosphorus from livestock farm. And crop production has increased over the year, primarily due to increase of crop yields and introducing new cropping varieties. Then with these input and output data, we calculated phosphorus surplus. So these bar diagram shows the mean value of phosphorus inputs and outputs for all counties in Lake Erie Basin. The black and white line is the mean surplus over the time. So if you look at the line, the phosphorus surplus started to increase mostly after 1940, after the increase of synthetic fertilizer, which is represented by the green bar. It's clearly visible the fertilizer is the major phosphorus input to the basin. So the annual phosphorus surplus peaked between 1970s to late 80s. However, due to the ban of phosphorus from the detergent and increase of crop yield, phosphorus surplus has declined after 1980s. At present, a significant number of counties exhibit negative surplus. So it shows by the gray areas in the right maps. These indicates, the gray areas indicate phosphorus deficit areas. It means more phosphorus is taken up by the crop than its input. And these are the location with the high crop production rates. So despite the fact that phosphorus is deficit in most area and surplus is decreasing across the basin, recurring algal bloom is common occurrence. So it indicates that the present algal bloom is not only a result of the current phosphorus surpluses. Then To investigate further, we added phosphorus surplus from 1930 to 2016 to quantify the magnitude of phosphorus accumulation between these years. And we see accumulation across the watersheds. The warmer color here also indicates that more accumulation. So high phosphorus accumulation were observed in southern Ontario. And then we correspond it to the spatial distribution of inputs. And we observed that high manure input areas can correspond to the high legacy accumulation. So we also couple phosphorus surplus in stream phosphorus concentration, and we selected 10 watersheds, 5 in US and 5 in Canada across the basin. So among them, 4 are the fertilizer dominant watershed in US, and one is the waste dominant watershed, Cuyahoga River at US as well. So we observe a clockwise hysteresis loop for fertilizer dominated watershed in US, and rest 5 in Canada are livestock dominated watersheds, and we saw like reverse than fertilizer dominated watershed loop. So these are anti-clockwise loop that is shown in for livestock dominated watershed. Now, let's pick 2 watersheds from each of the country of different categories, say Maumee River watershed and Grand River watershed at Canada. So first, we see Maumee River watershed. We see phosphorus surplus has reduced significantly over the year and is below 0 after 2000. However, when we plotted annual total phosphorus concentration, we see that total phosphorus concentration has not been improved as we should have been after reduction of phosphorus surplus. Thus, decreasing phosphorus surplus with increased phosphorus concentration can result a clockwise hysteresis loop for this watershed. And these can attribute to legacy phosphorus that have been accumulated in the soil over the several decades of agricultural activities. Then when we go to Grand River watersheds, the watershed shows increasing phosphorus surplus with the decreasing total phosphorus concentration, which resulted an anti-clockwise hysteresis loop here. So the takeaway message is we developed 87 years of transboundary phosphorus budget for the counties of Lake Erie, and we saw the changes in input-output trajectories over the time. American watersheds are mostly fertilizer dominated, and Canadian watersheds are livestock manure dominated, and higher legacy phosphorus accumulation was observed in agricultural areas, particularly in high livestock density areas. So we observe hysteresis relationship between total phosphorus surpluses and total phosphorus concentration, and that can signal the effect from legacy store. And as a next step, what we are doing now, we are using this surplus and developing a process-based model to estimate the legacy storage within the landscape, which can help to further analyze where the legacies are stored in our landscape. Thank you so much.
Thank you, Lamisa. So we're just right on time for that talk. So again, if you have questions, you can add them into the chat. You can even send them directly to Lamisa. And we'll just continue right along, continuing our discussion on phosphorus, but shifting gears to talk about wetlands with Emily Uri.
Hi, can you hear me and see my screen?
Yes, we can.
Great, yeah, so we're shifting gears to talk about wetlands. Oops, for some reason I can't advance my slides.
You
there we
may
go.
At the bottom, yeah, okay, perfect.
All right, my name's Emily Uri. I'm a postdoctoral fellow at the University of Waterloo. And this work is work that I'm doing with my supervisor, Nandita Basu, and we're partnered with Ducks Unlimited. Ducks Unlimited are a major player in the world of wetland restoration, and obviously in the Great Lakes region, we are concerned about phosphorus loading to our waters. So the main question of this research is how can we use wetlands to improve surface water quality and reduce some of this, the harmful algal blooms and eutrophication problems experienced in our lakes, such as the one that's been talked about a lot in this session in Lake Erie. So There have been numerous literature studies that demonstrate that wetlands are really powerful for improving water quality from nutrients. But I think that story tends to get a little bit overshadowed by nitrogen. We know that wetlands are fairly effective at removing nitrogen from surface water. And the story for phosphorus is actually much less straightforward. In these reviews, we tend to see a really large range in how well wetlands perform at removing phosphorus. And some wetlands even behave as a source of phosphorus to downstream water. So there's a lot of uncertainty surrounding what drives that source behavior and what drives wetlands to be poor performers at retaining phosphorus. And there's a lot of uncertainty surrounding the different phosphorus speciation. I'll be referring to total phosphorus in the rest of the talk as TP and soluble reactive phosphorus as SRP. And that's the fraction of phosphorus that is more readily bioavailable and more directly contributes to those algal blooms and water quality problems. So that's really one that we're concerned about when it comes to wetland retention. So this brings us to the main questions of my research, which is how prevalent is phosphorus source behavior in wetlands and what drives that source behavior? Are wetlands more likely to be a source of TP or SRP? And how can we improve wetland restoration and creation for better phosphorus retention? I conducted a meta-analysis that includes over 50 studies. Inclusion criteria were that the studies had to report an annual budget for both total phosphorus and soluble reactive phosphorus. And those 50 studies yielded 138 individual wetlands and 277 site years of data, so annual budgets. And that number 277 is kind of the unit that I'll be referring to in the results that I'm about to present. You can see those wetlands are not really well distributed globally, but they're more in North America and Europe. We also looked primarily at wetlands and agricultural catchments, but also included wetlands that are intended for treating effluent from wastewater treatment plants and a few that are in urban settings. And we're looking primarily at those constructed and restored wetlands. That's what we're interested in terms of potential future placement of new wetlands, but we also included mesocosm studies if they were conducted outdoors and were larger than 1 meter square, and natural wetlands in the case when they're receiving artificial inputs. So they're natural wetlands, but their water is being pumped into them for the purpose of water quality improvement. Diving into results, so this is the proportion of those 277 site years of wetlands that are acting as a phosphorus sink versus a phosphorus source. You can see 16% of wetland site years are acting as a source for total phosphorus, and that number is even higher, 26% for soluble reactive phosphorus, that more bioavailable, potentially more harmful form. So I think that's a finding that we should really be paying attention to. We see that in all months of the year as well, though this is a much smaller subset of the data. The next couple of figures I'm going to show you focus on the retention of soluble reactive phosphorus versus total phosphorus. So that's soluble reactive phosphorus on the x-axis and TP on the y-axis. And what you're looking at in this upper right-hand quadrant of the plot is those wetlands that act as a sink for both forms. So they're removing somewhere between 0 and 100% of the phosphorus they're receiving, and moving towards 100 is what we would like. But as you can see, a lot of wetlands fall below the 0 line, meaning they're acting more as a source of phosphorus to receiving water. So these wetlands falling in quadrant 3 are acting as a source for both total phosphorus and soluble reactive phosphorus. And then quadrants 2 and 4 are acting as a source for one form and a sink for the other form. So the next series of plots I'm going to show you are just breaking up our wetland site years into these 4 quadrant plots. And we're just going to discuss what might be driving some of these behaviors as they're broken down by these 4 quadrants. So I'll leave this here as a reference. And the first driver I'm going to show you is wetland types. So those 4 types of wetlands that we looked at. You can see for our quadrant 1 wetlands, the ones that behave as a phosphorus sink, all 4 wetland types represented. When we look at the other 3 behaviors, those wetlands that are acting as a source for some form of phosphorus, now we see that mesocosms are really not showing up in this portion of the data. And that's, I find that's pretty interesting because there may be many reasons why mesocosms are outperforming other wetland types. In fact, they're some of the highest, best performing types of wetlands in this study set. But I think it's really telling because we use mesocosms in our models and in our building our understanding of how wetlands work. So it's just interesting to think about how that might be biasing our understanding of how well wetlands are able to remove phosphorus from surface water. The next potential driver I want to talk about is hydraulic regime. This is a description of how water is moving into wetlands at the inflow. So it can either be constant, like in effluent from a wastewater treatment plant that's pumping out the same amount of water every day, or it can be variable, like in a rain-fed system. And it can be either continuous all year round or intermittent, meaning the wetland inlet goes dry for periods of time. In our wetlands that behave like a sink for phosphorus, we see all of these hydraulic regimes represented. But when we look at our source behaving wetlands, now we definitely see more of a tendency towards those variable and intermittent conditions, which makes sense. If you have really big rainfall events, they may wash out your total phosphorus. Also during dry periods, you may have oxidation of organic phosphorus in sediments of wetlands that become oxic, and then they may flush out in the next rain event. So I think these are important things to consider when designing future wetland construction projects. The next and final driver I want to discuss is the concentration of phosphorus at the inlet. The theory here being that at low concentrations of phosphorus, we might see phosphorus source behavior due to equilibrium interactions between the sediment and the overlying water. And in fact, when you look at those source behaving wetlands, you do see somewhat of a trend for the lower influent phosphorus concentrations leading to more source behavior. So I know that I'm pushing my time limit, so I'm just going to skip to my conclusion slide and say that this is definitely something that we need to, we need more work done on this. We're currently trying to model it. It would be really helpful in future if we had more new defined scale, especially temporal scale nutrient budgets of these wetlands, but overall integrating what we know from this meta-analysis with how we approach wetland restoration in the future has potential for improving water quality in our lakes. So I'll end my share there.
Thanks, Emily. Super interesting. I'm sure there are probably some questions. People can feel free to put those in the chat. And we will just keep rolling and move right on to Arisha Imran, who I see is here, ready to go. And it looks good. We can see it.
Okay, awesome. So hi, everyone. My name is Arisha, and I will be talking about assessing the legacy effects of large-scale flooding in 2020 on hydromineralogical conditions of lakes in the Peace Athabasca Delta. Oops. Okay, so the Peace Athabasca Delta is located in northern Alberta. It's a Ramsar site of international importance. The Delta contains thousands of shallow productive lakes and wetlands, which provide important habitat for local and migratory fauna. Lakes within the Delta can span the hydrological gradient from being open, restricted, or closed drainage, depending on their level of connectivity to river channels. The Delta also lies within Wood Buffalo National Park, which is a UNESCO World Heritage Site and contains traditional territory for Indigenous and local cultures. So the Peace Athabasca Delta, also I'll probably call it the PAD in the presentation, is threatened by multiple stressors. One of those stressors is climate change, which continues to alter the seasonal distribution of precipitation by shortening the duration of seasonal ice cover and increasing the rate of evaporation. Upstream regulation of hydroelectricity also alters the seasonal distribution of discharge, and water withdrawal for oil sands production reduces discharge as well. So all of these stressors have been linked to declining lake and river levels during recent decades, yet no comprehensive aquatic ecosystem monitoring program was in place for lakes in this landscape. So this leads me to briefly discuss the motivation behind what led to monitoring in the PAD. So in 2014, the Mikisew Cree First Nation petitioned the World Heritage Committee to list Wood Buffalo National Park as a UNESCO site in danger due to concerns around lake drying in the PAD. And then in 2017, the World Heritage Committee responded to this petition and provided a list of 17 recommendations to develop a well-structured response. And then in 2019, Parks Canada released a collaborative action plan with specific actions to ensure the protection and maintenance of the outstanding universal value of the park. So where we come in is in 2015. So when the Hall-Wolf Research Group had already designed a monitoring framework for the PAD in tandem with what was already going on. And this was tested up until 2019. And in 2020 and 2021, Parks Canada and members of community-based monitoring programs sampled the lakes. And this is a great transition towards, great transition from university-based research to agency and community-led monitoring. So one example of how our work has aligned so well with the World Heritage Committee recommendations and the action plan is by taking a look at recommendation number 7, for instance, which deals with establishing baseline hydrological information for improving monitoring. So this recommendation resulted in 75 actions, and here are a few examples of some specific actions that our previous work has contributed towards informing. For instance, identifying key priority areas experiencing drying, assessing rechargeability of high elevation basins, identifying and filling knowledge gaps, and conducting spatial and temporal analyses. So here are 2 products that came out of our monitoring framework that I previously mentioned, and these have directly contributed to some of the actions from the action plan. So we've been able to map the 2018 spring flood on the left, and we've also mapped these isoscapes from 2015 to 2019 on the right. And the isoscapes are showing us areas where lakes are most influenced by evaporative water loss, represented by the warmer colors, and areas influenced by river floodwaters or precipitation, represented by the cooler colors. So the flood map is showing us areas in the delta where river floodwaters were able to reach, and the isoscapes are showing us quite a few seasons and years were dry, and we see that the springs of 2017 and 2019 were relatively wetter. So why is that important? So in 2020, there was substantial flooding, and you can see that here in the satellite imageries. So the image with more blue and clouds is 2020, so this image, and when compared to a dry year, which is this image, like 2017, which in this case was the image with more green, you could see that there's a drastic amount of flooding over the summer in 2020. So we can also see that through these isoscapes that 2020 was a pretty wet year. And where I come in is 2021. So I'm looking at the post conditions of 2020 on the hydrolimnological conditions of lakes in 2021 and seeing if there are any legacy effects of that year. So although there's been a lot of focus on areas of the delta where ecological integrity may be compromised because of decline in freshwater availability, there has been far less attention to the effects of the rare suite of conditions that prevailed during 2020 and what their legacy effects may be. So I'll be doing that using water isotope tracers, water level loggers, and water quality and chemistry data. And this will also inform the actions outlined in the federal action plan. So here we have the 2021 ice escapes, and they also indicate exceptionally wet conditions and correspondingly low influence of evaporation despite warm temperatures in summer of 2021. So when compared to the 5-year ice escapes, we can see that 2020 and 2021 are the most wet years for the Delta over the past 7 years. And some of my next steps included distinguishing which lakes flooded in 2021, determining the proportion of input water and the source, and also characterizing the range of limnological conditions in 2021, which I hope to present next time. Thank you.
Thanks very much, Arisha. I don't know if there's any questions. We do have a little bit of time. If anyone has a question, you can feel free to unmute yourself. Just while we're waiting, I guess from this picture that yes, but were you actually out there in 2021 doing the sampling?
Not in 2021. So 2020 and 2021, we were able to work with Parks Canada and community-based monitoring groups there to sample these lakes for us. So it was a great collaboration effort. And we're really thankful that they were able to sample because we wouldn't have been able to capture these conditions then.
Yeah, definitely. The last 2 years have not been the easiest for field work. So I'm glad you were able to get that data. And I think it's so important to also be sort of, when we are trying to understand disturbances, having those great comparator, not as disturbed systems so we can understand that natural variation. So it sounds like I'll be excited to see what you find and are able to present next year.
Thank you.
Any questions from the audience? Not seeing anyone jump up, so I think we can get back on time and move on to our next presenter, who is Sarah Kaikraj. I practiced this one and I still can't get it. Kaishkravi. No, I still did it wrong.
Hello.
Hello. And you'll be bringing us a little bit back, Sarah, to talking about phosphorus in an urban environment.
Sure. Nobody gets it right. It's okay. Thank you. Hi, everyone. Hi, Maria.
Right.
So is it shared now?
It is. Yeah, looks good.
Looks good. Okay. I'm going to, oh, sorry. Hello, everyone. My name is Sarah. I'm a postdoctoral fellow at the University of Waterloo Ecohydrology Group. Today, I'm going to talk about a phosphorus model that we have developed to predict urban phosphorus export into urban sewersheds. First, I would like to acknowledge all who had helped me during this research. And if you need to contact me, that is my email for any question. Please feel free to email me. As the beginning, I'm going to start off with an outline about today's talk. So I start with an introduction, then study area, following with a little bit talk about the modeling approach and presenting the results and conclusion, all in brief. So I'm going to start off with an introduction to the subject, including the water quality models, what type of models, and quality parameters and calibration. Usually a deep insight to the water quality dynamic is attained through lab experiments, real system samples, but this is not the case when it comes to a large scale model, a large scale case study, which could be an urban sewersheds that is usually coped with through water quality models. There are different quality models, including regression, machine learning, kinetic empirical models, which vary in terms of how they can be generalized, also what amount of data they need. In this study, we have used empirical model because they allow to better generalization. Also, they need the least amount of data. And in a specific case, we are using a stormwater management model, which is known as SWAM also. And water quality parameters has been studied for like a wide range of them, from sulfide, which has been the most studied, to iodine as a parameter that has been the least studied. Phosphorus in between is one of the cases that affect eutrophication. So today we heard about eutrophication. I'm not going to go through all that again. So that's why we are studying phosphorus export, and because we are at the long term, we want to mitigate the eutrophication effect of phosphorus in urban settings. And also about the calibration of water quality models. According to one study, which is a big claim, there's none of the urban water quality models, there's none calibrated. So this study that I have talked about is like a very recent review about water quality modeling in storm sewer networks, published a couple months ago in Elsevier by Gia et al. So it had two nice figures, which I like to share with you with some information. Three-form information which appealed to me. One is that the extent of the different model that has been used during the past literature, like the past studies, which from the regression to the empirical and kinetic, we could see that the empirical model for different water quality species are most favorite. And the most parameter has been studies, like I mentioned, the sulfide, the sediment, COD, TSS, and we could see that phosphorus is among all parameter that has been least studied. Also, the experimental and field samples for phosphorus has been more of attention, but continuous modeling of phosphorus is, you could see that there's zero paper about it. So least addressed among all. About the calibration, most of the water quality models has not been completely calibrated, and the calibration of these models is a big of a challenge. So especially for P, which I'm going to talk about today, we could see that there is not, there's like a limited studies about it, not available. So the objective of this study, like I mentioned, is estimating urban P. Today I will talk about like total phosphorus, total dissolved phosphorus, and dissolved reactive phosphorus export, which we have done through a numerical modeling. This study area is located east of GTA, City of Toronto, north of the Lake Ontario. So in the long term, we are going to study these four cities shaded in solid color, white. But right now, today, I'm going to talk about these two watersheds, which one of our presenters, Mahir, talked about it before. So we have sampled these two watersheds, one shaded in gray, one is in white. We had a monitoring location down the stream, single monitoring location for each of these, and have sampled these for more than 1 year. So we have used these sampling data to calibrate the model. A brief introduction to this study area is that, so the area for both is about 250 hectares. The stormwater of these study area are collected through pipeline, and they have about 30 kilometers of pipeline. We got to model them about 8.3 kilometers. Also, we modeled the main pipeline range from 0.6 to 2, and annual rainfall of these two watersheds is 677 millimeters. What we have started is that we created the model and followed all the standard modeling procedure. So next step was calibration. For the model calibration, we have selected the modeling period to be continuous historical. Like I said, we wanted to calculate annual load for the P export. For the modeling time step, there are a wide range of time steps that we could use, but we started with sub-daily, and we stick to that because urban stormwater collection network are fast responders, event responders, so that better suit our purposes. And for the performance time step, usually observed data determines that, and that was our main challenge. So because we lacked significant continuous data for our performance model, particularly regarding the sample models or sample data. And for the performance metric, we have used R-square, NSE, SCE. How to calculate that? There are a range of methods to do so. You could use exact value, or you could use a range of statistics against your model statistics. So I'll explain that in the next step. First, I want to refer to the challenges of the data that we had, the observed data that we had. So we needed to adjust for that and cope with that challenges to be able to calibrate the model. First of all, it was the lack of continuous data. So in the flow, usually it's better because we had like continuous gauge. But about the sample data, it was much worse about the quality samples. So like you see, these are two examples. One is representing the left side, representing a better sample data for the P models. It's P data, TDP, TP, and DRP. We could see that they nicely are along the event, although they don't have equal intervals or and the intervals are long, but still much better showing the pattern. But unfortunately, most of the data that we have are similar to the right side. So we could see that for this specific event, we don't have flow data. Also, there are like limited number of the P samples. And so what we have done, like we started off with a standard common procedure, but we had to just cope with step by step. I go through that very quickly. So imagine that this is a timeline and there are different events. Within each event, the black solid are the model, the red one are the sample data. So what we had, the black dots showing the number of the model data, and the red dots are the number of the sample data. We could see that like the amount of the sample data that we have are much less. So in the first case, all the performance metrics, even if you have a perfect model, the performance metric with these kind of data would be low. The next step, like we have practiced, was dropping non-values to have equal number of values. But it still didn't work because the timestamp did have uncertainty. So we had to cope with that somehow. We started off with using a statistic within timestamp, which we selected as our approach to be event-based. I don't have time to go through the detail today, but that was the best choice compared with the other common choices. So the mean of the data didn't work in here because that is not how, it's not able to represent the reality. So we decided to use the maximum of the data, which represent the maximum load exported through each event. So other data were filtered out, just the data that were about the maximum flow were selected to compute the estimate the performance metric.
So Sarah, you're just about out of time. So if you can sort of wrap up
sorry.
in a minute or two.
Yeah, sorry. I'll wrap it up. So the next was the regression model that we have developed. And this is another step that we was a breakthrough during this calibration and the calibration matrix. Just a quick view to the flow, which you see that the calibration and the model are corresponding well. Also the calibration of the parameter and the model shows that even the pattern of the sample data has been simulated in the model very well. So the high NSE and R-square values. And we were able to calculate P loads, and I don't have time to explain that. So at the end of the day, we were able to compensate for the lack of many uncertainties and intermittent data with our different approaches, and finally come up with an event-based approach and calculate TDP, DRP, and TP for these urban settings. And I believe that this method can be used for other urban spillwater collection networks. at the end, thank you, and thank you all the sponsors and my supervisor, Dr. Philip Van Coupland, and also my colleagues who helped me with this study. Thank you.
Thanks very much, Sarah, and looks like an exciting advance in the modeling of urban systems there. So if there are questions, feel free to put them in the chat. We'll continue right away to Julie Terry, who's going to switch gears away from phosphorus a little bit, I think, but maybe I'm wrong, Julie.
Hi, can you see my screen okay?
Yes, we can.
Okay, excellent. Yes, I'm actually going to bring you back right down to Saskatchewan. So I am working at the Global Institute for Water Security, and I am modeling Buffalo Pound Lake, which is in the Upper Capel River Basin, and that's next to the Saskatchewan River Basin. So I'm working in collaboration with the Water Security Agency and the Buffalo Pound Water Treatment Plant. And these are two organizations that have been incredibly interested and open in working with the Global Institute for Water Security, or GWF. And they are currently acting as both my data providers and the end users of my research. So part of their mandate is the provision of safe, clean drinking water from Buffalo Pound Lake for around 25% of the Saskatchewan population. Now, some of you may have seen this slide before, but these articles are from May 2015. And what happened was you had poor water quality entering Buffalo Pound during spring freshet, combined with unusual mild, calm spring weather. And that led to an unusual spring stratification event of up to 8 degrees gradient. And that was very unusual for this time of year. And it led to complications in the water treatment because the warm water was entering the clarifiers, rising to the top, carrying the flock to the top before it could settle out. This led to a delay in treating the water, which subsequently led to water restrictions in the cities of Moose Jaw and the provincial capital, Regina. So part of the way in which we are collaborating is having discussions in how we can assist each other in the model application. So here you see the bathymetry for Buffalo Pound Lake. It's a very long, narrow, skinny, impounded lake. It's about 30 kilometers long, averages about 1 kilometer wide. And in my original bathymetry for my PhD, I did not include a 4-kilometer shallow section above Highway 2, which you can see in the red circle there. And the reason it was not included was because there was less certainty in the bathymetry when it was interpolated from the sonar data, because it was too shallow for the boat to enter and collect many data points. However, this in turn led to some uncertainty in the actual modeling results because the water quality monitoring stations and the flow stations are both above that 4-kilometer section of lake. And so there was some discrepancy between the nutrient concentrations and flows entering into the main body of the lake. And so the Water Security Agency were very keen for me to try and incorporate this extra 4 kilometers of bathymetry. And so the way in which they assisted me was they went out and collected lots of additional profiled sampling data of the water quality constituents, which they provided me. This then allowed me to include the extended model grid and test the bathymetry and validate the kind of model calibration. And so that was just one of the ways in which we've been working together to find solutions. So the initial steps I've been taking have to model the water quality in Buffalo Pound using Sequel W2, which is a 2-dimensional hydrological ecological model. And Buffalo Pound Lake mainly receives water from Lake Diefenbaker upstream as managed flows. However, during high precipitation events and during spring freshet, you get large volume of water from uncontrolled runoff in some years. Now, it's very variable and it does depend a lot on the antecedent soil moisture conditions and the fullness of the wetlands. But when it does happen, it can become a substantial amount that's coming in with runoff, and it's very poor water quality. Lake Diefenbaker, in contrast, receives most of its water from the Rockies, and it's much better quality water. And both the Water Security Agency and the Buffalo Pound Water Treatment Plant have been interested in finding out if additional water transfers from Lake Diefenbaker would help improve the water quality in Buffalo Pound after these runoff events. Now, this was tested in 2015 after those slides that I showed you, but it was only run for a few days and it didn't have much impact, really, because it wasn't much volume of water. But this is in addition to the fact that the population is increasing and there's now climate change causing extra stresses. And so they are very interested in, examining situations of augmenting the water supply from Lake Diefenbaker to Buffalo Pound Lake. So basically, I have been modeling water scenarios, and basically I have been looking at the impact of releasing additional water from Buffalo Pound in my model. I'm sorry, I'm just having a few technical hitches. Just give me 1 second. Okay, so so basically, just quickly going back. So I have been modeling the impact of longer term water transfers from Lake Diefenbaker, because as I was trying to say, the Water Security Agency cannot just release lots of additional water straight down the Upper Capel River channel into Buffalo Pound to flush the water, because it's a very shallow system with there's a maximum channel capacity, and they have to be very careful not to flood the area. And so really it is a question of optimal timing, is how and when best to release the water transfers of this considerably better water quality to help flush the lake. So that is what I have been modeling. And what you can see here in these results at the bottom on the left-hand side are just some of the differences in mean total nitrogen concentrations over 6.5 years with the different scenarios. So I was initially working with just the SQL-W2 model of Buffalo Pound Lake. And I was using a very simple regression method to estimate the nutrient transformations from Lake Diefenbaker to Buffalo Pound Lake. But I wanted to see if I could improve these. Now, there was already an existing one-dimensional WASP model that existed, developed by my colleague Nazim for the Upper Capel and Buffalo Pound Lake. So that was developed for a different period. So I took that model and I updated it with newer data, and I used that to model the nutrients all the way from Lake Diefenbaker right down through the lake to the Buffalo Pound water treatment plant intake. I tested that, and then I essentially replaced the lake part of that 1D model with my own SQL-W2 two-dimensional model, because what I wanted to do was compare the output. So it's kind of a loose model coupling in that I'm taking the outputs from the WASP model at the point where the river ends, and I am using those for my boundary conditions for the SQL-W2 model. And then the plots that you see there in the top right are the calibration results at this kind of river-lake interface for a couple of the constituents. And I have been looking at the differences between the two models for this lake section and comparing. So I think it's possibly worth mentioning at this point that Buffalo Pound Lake is a very challenging lake to model, and it's very reactive to climate conditions and through flow. It's a shallow lake and it's relatively high through flow for a lake. So I'm still there is kind of work in progress for the calibration, but you can see that there is some differences between how the 1D and 2D modeling is currently representing the conditions at the intake treatment plant. And then once I'm happy with this calibration, I will be using the River Lake model to investigate a few scenarios that have been suggested by the Water Security Agency and the Buffalo Pound water treatment plant. So they both have some scenarios that are of interest, and particularly I will be concentrating on flow management and climate change, which are the next areas I will be looking at. So I'm going to stop sharing my screen there. I apologize for the technical hitches. I had a bar pop up on my screen. I wasn't sure if you could see that or not. It kind of put me off slightly.
No.
It was a Zoom thing. Okay.
No problem. You were right
Okay,
on time.
no
Yeah,
problem.
you were right on time though, so
Okay,
no
great.
problem. I think we're just about right on time. So if there are questions for Julie, you could add them to the chat. And we'll continue on to our last presenter before our couple of lightning talks. So do stick around for the lightning talks. So I'll pass it over to Rushi Bhattacharya now. And you can go ahead and share your screen. Looks good.
Hi, everyone. Thank you so much for tuning in. My name is Dr. Ruchi Bhattacharya. I'm a postdoc at University of Waterloo with Dr. Nandita Basu. And today I'll be talking about lakes and reservoirs as integrated archives of watershed disturbance and phosphorus legacies at centennial scale. So we have talked a lot about phosphorus loading, and we know it's a challenge in aquatic systems. And despite decades of efforts, we have not reached the water quality levels that we wish. And it's often linked to legacy nutrient deposits. And you've also heard a lot about legacy nutrient deposits, and we know that they are just surplus phosphorus that accumulates across watersheds and in lakes and reservoirs, sediments that can derail our water management efforts. There's been a lot of work in terms of understanding how watershed deposits of legacy nutrients affect water quality, but still there are knowledge gaps that exist in terms of knowing what is the magnitude and spatial patterns of legacy phosphorus in lake ecosystems, and what are the factors that drive them. So in order to answer these questions, I used a meta-analysis approach, and I explored the century scale trajectories of lake sediment phosphorus in lakes across the world, and then related these to trajectories of watershed disturbance. I used an approach where I said using meta-analysis of paleolimnological studies, so lake sediment records of phosphorus accumulation that have been dated by radioisotopes. So you have a chronological history of past 100 years that you can use to understand how phosphorus evolved in lake ecosystems and their watersheds. And then we delineated watersheds for each of these lakes and found out information about the morphometry. So for instance, lake depth and watershed to lake areas. And finally, use this information to then find out information about watershed disturbance trajectories. So for instance, percent of crop, how that has changed through times, population density, fertilizer applications from 1900 till say 2016. This is just a map of all the study sites. We have a total of 145 lakes. And here I am color-coded them based on the max depth. And if you look at the gradient or the legend, you see a lot of the lakes are actually shallow. They're quite shallow, and they're located in Northern Hemisphere mostly. We found that a lot of the lakes are also less impacted and had like percent crop much less than 50% in their watersheds. Now, using machine learning based techniques, I was able to find out distinct clusters of lake phosphorus sediment trajectories. And here I'm showing the 5 clusters that have been color coded. Just to point your attention to the orange dots in China, for instance, that represents cluster 2, and the green fill dots in UK and Ireland that represents cluster 3 and 4. So if you look at the trajectories per se, and here I'm showing the median sediment phosphorus trajectories from 1900 till 2016, you can see that there are distinct patterns that emerge. For sake of time, I'm going to be talking just about 2 of them today. So if you focus on the green line here, it represents lakes that are located in developed countries, so North America and Europe, for instance. And what's unique about them is that all of these lakes kind of had a very early onset of phosphorus loading that was followed by a ramp up in phosphorus concentration in lakes from 1960s till say 1970s and 80s, followed by a bust in phosphorus concentration that was driven by bans in phosphorus laden detergents and wastewater treatment plant implementation. But when you compare that with the orange line, which represents lakes located in transit countries or developing countries, they had a relatively lower or later onset of phosphorus loading, but there was a ramp up in the amount of phosphorus concentration in these lakes and accumulation post 2000s, and it's increasing as we speak. The next step was obviously to find out what's driving that, and I looked at all the drivers I had kind of mentioned earlier, but here I'm going to be talking mostly about phosphorus fertilizer application for the two clusters I just talked about. So more specifically, we found that fertilizer application, when it was normalized by watershed to lake area, it was the best predictor for sediment P accumulation. And you can see that the green line here that represents phosphorus fertilizer application in developed countries kind of tracks very nicely with the sediment P concentration trajectories that you just saw. Whereas the orange line, it mimics what the sediment phosphorus concentration trajectories were seen for the developing countries. So, so looking at now at a more of a lake level, you can see that, again, these are the 145 lakes, and they have been color-coded based on the amount of sediment phosphorus accumulation. So if you look at the legend, the purples mostly are located in European countries, mostly UK and Ireland, for instance, and the oranges and the yellows are a lot of them are located in China, for instance. We also have a lot of dark reds in North America, which represents a higher amount of phosphorus accumulation. So what's interesting here is that even though in North American or European countries, there was a decrease in the external loading of phosphorus, you still see a higher amount of phosphorus accumulation in these lakes, which speaks to the role of watershed disturbance legacies that kind of driving that. And in China and other agriculturally dominated places in Asia, for instance, you see that even though the onset of watershed disturbance was relatively newer, but they are kind of very quickly becoming the hotspots of water quality issues and newer sites for phosphorus accumulations. Now, again, carrying on with the lake level assessment, and this is a principal components analysis. I know there's a lot going on. If you've not seen one before, I would just bring your attention to a couple of things here. So if you focus on the orange dots here, which mostly represents, in this case, lakes in UK, they are located across the axis of depth. So it shows that they are mostly shallower lakes, and they have a greater watershed to lake area contribution. So it means that they have a greater watershed contribution. Now, these lakes tended to have a higher amount of sediment phosphorus accumulation in them. Now, if you compare that with the green dots, which represents the lakes in China, they're all clustered together, have a relatively lower sediment phosphorus accumulation, but they're mostly driven by higher concentrations of crop population and fertilizer application. So you can see that at both cluster level as well as lake level, which shows a cumulative accumulation from 1900s till 2016, there are different patterns that emerge between developing and in transit countries and developed countries. So very quickly to summarize then. So we found that the timing of onset of watershed disturbance matters a lot, but you also have to think about the morphology of the watershed and the reservoirs or lakes in their role in driving phosphorus accumulation trajectories. The legacy of phosphorus disturbances play a big role, and their effects persist even though the external loading has sort of decreased. Next, if you remember back to the first map, we saw a lot of the studies were mostly in North America or in the developed world, so to speak. So we need more studies from the global south or from developing countries that are more agriculturally impacted in order to get a better picture, a broader sense of what is happening in terms of phosphorus legacy accumulations and how would that impact these systems moving on. And finally, I would have to thank all the amazing undergrads and co-ops and master students who have worked on this project and spent hours upon hours of time digitizing information, delineating watersheds, and collating this data set together. This data set will be available once the project is complete and should be a great resource, we feel, for testing management, for effectively designing management strategies, and for also validating watershed nutrient transport models. So that's all I have for today. If you have any questions, please feel free to ask or send me a DM. Thank you.
Yeah, thanks a lot, Rushi. You're just about right on time. I don't know, we have maybe 1 minute if
Okay.
anyone has a question. I'm going to take my chance then and say, I guess you said you didn't have very many points yet from the south, or from sort of more of a equatorial region, really. But I was wondering if you have seen already, if there a difference in the rate at which phosphorus, you see changes in the phosphorus concentrations in the lakes with your sort of fertilizer application, depending on where you are climatologically?
Yeah, so for this project, we haven't yet explored the climatological roles of it. So it'll be interesting to see like how, changes in, winter precipitation and lake ice changes, and, having more droughts in say the global south, for instance, how would that drive these patterns, and role of external loading versus internal loading. So processes where phosphorus is coming in would change, I would think, and it would be interesting to see. So even though we have maybe a couple of studies from Africa, some from China, even though they have more recent external increases in external loading, but if you see more of droughts, for instance, we would imagine all the legacy phosphorus is going to be loading up into the water column and lead to algal blooms and eutrophication. So yeah, that's definitely something that we are looking into now, and hopefully have more to report soon.
So like you said, that database will be great, and be able to answer a lot of questions moving forward, and hopefully be added to.
And it's also constantly being built. So there are other aspects of it in terms of model phosphorus that people have from biological indicators. So there's a lot of data. This is just the tip of the iceberg. So there's more exciting things to come.
Great, thanks so much. So now we get to move on to 2 lightning talks that we have in our session here. And so the first one is from Erica Burton, who's going to talk about optimizing environmental DNA detection protocols. Erica, you just need to unmute, I think.
Can you hear me all right?
I can hear you now, yes.
Perfect. Okay, 1 second. Okay, well, thank you all for having me. I'm here to kind of crash your nutrient panel to convince you to come talk to me about fish. So generally, I would like to kind of pitch my poster. The issue that I was trying to address with my research was a way to sample remote aquatic systems, since traditional techniques for fishing and other kind of sampling can be very difficult in remote settings. And there's also a lot of hazards associated, like debris in the river. A potential solution to this issue is a lot of emerging techniques regarding the detection of environmental DNA. So eDNA, or environmental DNA, is when an organism basically sheds its DNA into its environment. So for fish, that's through mucus or feces or sloughing cells. And then you can collect a water sample and determine if your species of interest is there. So this is a very promising technique for remote areas, but still needed some validation. So I performed, in collaboration, of course, with some researchers in Chile, a pilot study in Chilean Patagonia, sampling 6 different rivers for environmental DNA of 3 different fish species that were of interest. And I wanted to determine how feasible the method is, and if I was able to detect whether these fish were present in uncharacterized rivers where they hadn't been previously sampled. So I was able to detect both brown trout and a native species in some of these rivers, and make some conclusions about the feasibility and efficacy of using environmental DNA as an alternative to more traditional fishing techniques in remote areas. So I would love if anyone would come chat with me tomorrow at the poster session. Thank you.
Great. Thanks, Erica, very much. And then our last speaker and last lightning talk of the day is from Ali Reza Shavaran.
Yes.
So take it away.
Thank you. Can you see my screen?
It's coming. Hold on. I don't know. It's very slow. Oh, there it is. I see it.
Okay, thank you. So I don't know why it's keep. Okay, so the title of my poster is long-term monitoring of algal. I don't know why it should be fine. Long-term monitoring of algal biomass in Western Lake on, oh God. There's something like with the.
It doesn't, yeah, I guess it doesn't want to go to the, like the.
Okay, I just presented from here. The title.
That should be fine. Oh, it's trying.
God.
I think maybe the file is so large that it's not happy. We can see it from this mode, okay?
Okay,
yeah.
I have no idea. Okay, the title of my poster is Long-Term Monitoring of Algal Biomass in Western Lake Ontario using remote sensing imagery and in situ data. Lake Ontario provides drinking water to more than 9 million people. Historically, water quality problems in Western Lake Ontario, Canada's most densely populated region, have been caused by urban, rural, and sources and discharges from upstream Lake Erie that carry nutrients and sediments into the water. Drivers of algal blooms in this region are mainly population growth and urbanization, ecosystem changes, and global warming. And in order to develop climate adaptive management strategies to mitigate the effects of eutrophication in Western Lake Ontario, it is necessary to have a solid understanding of the spatial and temporal dynamics of algal blooms and the hotspots in this region. So what I do is basically using the satellite imagery, specifically in the visible and infrared bands from Sentinel-2, Landsat 8, 7, and 5, and also coupled with drone images, which has higher spatial resolutions of 8 centimeters. And I use empirical algorithms in mostly infrared, red, and green bands, because chlorophyll A pigments have high reflectance in near infrared and red wavelengths and high absorbance in green. So they have unique spectral signature. By combining visible and infrared band of satellite images, we can detect presence and also estimate concentration of chlorophyll A in water pixels. Then we use institute data to calibrate and validate our models. In the upcoming weeks, we'll be conducting fieldworks to collect more institute data using spectrophotometry and fluorometry methods for chlorophyll A concentration, and also in the dates that we have both satellite and drone overpasses. And then we will begin analyzing the data. Thank you. Sorry for the problem with the PowerPoint.
No problem. Thanks,
okay.
And great job continuing even with the technical difficulties. So I just want to remind everyone that you can go and view the posters at any time, but there are poster sessions tomorrow. Presenters will be grouped into clusters, and both Erica and Ali, who you saw here, are in a cluster called Water Quality and Aquatic Ecosystems, if you want to chat with them more. So just before we wrap up the session, I think we should give all of the presenters a round of applause. You can do that virtually. You can feel free to turn your camera on and do it as much in person as possible, but thanks to all the presenters. Great job. It's always hard to present to a blank screen and with your technical difficulties, but you all did a great job, and thanks for staying on time. So I hope everyone has a great rest of your afternoon or start to your afternoon, depending on which time zone you're on, and enjoy the rest of the meeting. Thanks.
Thank you. Thank you, Maria.
Thank you.
Thank you and bye.